Let me start. Hi, I'm Fred Calef. I'm from JPL, for those of you who don't know me, and I am a geologist by training. I am a data scientist by title, uh, but really it means that I work with base maps and various geospatial data sets in helping missions, specifically Mars missions, at JPL, as well as helping landing site analysis and a few other things on the side. My background is really coming as a geologist and wanting to be able to share scientific data with other team members and allow them to make decisions. So I was brought on as a postdoc at JPL to help with landing site analysis for MSL. The Curiosity Rover, and that evolved into a position as the quote-unquote keeper of the maps for that mission, which meant I was in charge of all the geospatial things and keeping track of science targets and answering scientists' questions about, how tall is that feature? How far away is that? How are these observations spread out along a mapping interface, along a map? And rapidly figured out that I was the blockage to them getting those answers, and so I asked the NASA Advanced Multi-Mission Operations Systems (AMOS) that is run out of JPL if I could develop this project called MMGIS, which is a web-based mapping system. And they said yes, and so that's what I'm going to talk to you about today. And just to note, some of my co-authors, Tarek Solomon, he's the primary developer for MMGIS. And he's online today, and so he can answer some of the very deep technical questions, but he's been in from the beginning and is brilliant. And also Hallie Abarca, who helped with some of the localization scripts that we're using on Curiosity and we'll be using for 2020. So what's the problem? Scientists are smart, but they're not all smart mappers. Probably not surprising for this community that mapping is an incredible technique and it requires a very special skill set, just as spectroscopy or seismology, all those other disciplines, geochemistry, all those disciplines have their own specialties, their own techniques. Mapping is no different. So people want to see things on maps. People want to understand their context. So oftentimes we have these multiple co-registered data sets. Anything from elevation models to derived products like slope to machine vision, things like looking at rock density and such. And then, of course, all the other things that vector overlays that go with it. Where is the rover going to land? Where's the landing ellipse? Where is the nominal traverse path? So lots of data that we pull from orbit. And then we get all this in situ data. And as I said, so many instruments, so little time. It gets very tricky because each instrument has its own coordinate system in a relationship to the spacecraft or to the rover. And then that is all in relation to some map, some other global or planetary coordinate system. So, to dig through the 20 different reports and the various SISs that describe all these coordinate systems and uniting them into a actual point on a planet is really tricky. But it was interesting to step back and say, well, what does it mean to find out where something is on a planet? So it relates to the spacecraft, but all these spacecraft have somewhat similar ways of looking at data or similar ways of working their coordinate system. So we've broken it down into three, which is one is body fixed, which is basically just the instrument is attached to the body of the spacecraft. And as the spacecraft turns, the instrument turns, right? So imagine a camera mounted on the side of a spacecraft. If it's fixed and the orientation of the spacecraft determines the orientation of where that image is taken. Same thing for a rover, same thing for a lander. Then there are things that are on a mast that will change in azimuth and elevation independent of the spacecraft. And that's a whole other set of instruments, anything that swivels. And then there are contact instruments that are on some articulated arm where you have to do the kinematics and reverse kinematics to find out where that arm is in relation to the spacecraft and then to Mars. So lots of conversions there to figure out. And then there's the data that comes from these instruments. And sometimes, in case of like the ChemChem instrument on MSL, which is doing laser-induced breakdown spectroscopy. So it's getting back to spectra, and this is always the way it goes. The scientist says, "Huh, that's a really interesting result." Second question is, where is it? And that's where we hope MMGIS can come in to answer that question, so that the scientist can then ask the next question, or more importantly, in terms of science operations, make the next decision. Oh, we've seen this value of silica before, no big deal, let's move on. Oh, we've seen this value of silica is interesting, let's do more science here. And so it's cutting that distance between the time you take an observation and getting a result, and then making a decision based on that result that we're really trying to solve. So I'm going to talk a little bit about the architecture, because this is the group where I can do that. So basically we have, as our users, we have the science and engineering operations team. Those are our customers. And then this is all web-based system. So the client becomes your browser. You're not downloading software per se, you're pointing to your URL, and you're getting the same software that everyone else is getting. We develop on Chrome, as many people do. However, we do support Firefox and other browsers as long as they are WebGL compatible. And so far, it hasn't been too bad in terms of that cross-browser world. Occasionally, little things happen, but such is developing life. And on the back end, we have a server, which we were originally started with Apache as our base web server. We have now moved on to Node. We're almost, I think it would be, well, you could run a Apache version of the software. It's much easier to run it with Node, and it makes development a lot easier. And we can run the web server part of the software as a, on your laptop if you really want to, on some bare metal server. It is also pretty cloud friendly. In fact, for 2020, all of the web, well, yeah, almost all the web tool, all the tools are web based and are taking advantage of AWS and are supporting that type of cloud-based architecture. But we are very much an open source project, so everything you see here that we built is open source. We use GDAL, Python, and in the background, then we have JavaScript, of course, for our front-end client programming. And we support a variety of ways of getting our data into MMGIS and then serving it out. In terms of database support and really spatial database support, we're really finalizing on PostgreSQL and PostGIS. Theoretically, we could support really any spatial database like the SQLite Spatialite extension or MySQL. There might be a little tweak we might need because some of the commands aren't exactly all the same, but pretty much it's a pretty, so far I think we're using pretty standard calls. However, we can also import CSV files as data tables that we can then link to data within the spatial database. In terms of vector formats, we really began solidifying on GeoJSON. Now we are also supporting Macbox vector tiles that we serve out of the Postgres database. So we can, so instead of just being able to support thousands of features, we can now hit the larger numbers of tens of thousands or hundreds of thousands, which you might expect from an orbiter mission over time in terms of images on the ground. We can also import shapefiles and GeoJSON in different ways. And then for raster data, we're using GeoTIFF as our standard. We often, well, we always tile them up using the TMS tiling format, and that's served us pretty well. I'm going to move on and then just talk a little about the open source base. So this software is released on an external version of GitHub. If you Google NASA AMOS, which is AMMOS, and MMGIS, you will get to the current released version of the software. And so, so again, it's all open source, it's all released, it's under an Apache 2.0 license. We are using Leaflet for our 2D base map. We use 3JS to look at our kind of 3D globe view, and then a combination of other packages like D3, jQuery, Proj4 to do different conversions and showing the data. We do have an instrument localization pipeline. It's still being worked on. We've released some parts of it, but it really needs a little bit more work to kind of make it very generic, because we do tie into some local JPL tools to extract a few parameters, but that's a little bit being worked on. But in terms of, again, getting out data, GeoJSON either through Ogre or PostGIS to the conversions. Through PostGIS, we can serve out Mapbox vector tiles. We have a little wrapper script, raster tiles, which wraps around G-delta tiles just to allow us to build the tile format independent of what the planet is or the planetary body. And then we have another script called raster tiles, and this is 1B to 4B, which has to do something with the way the tiles are shaped. But basically, we're using that same TMS tile format, but we're encoding them as 32-bit RBGA pings. So that way we can actually encode floating point data into a tile format that replicates all the other tile formats that we use, and then we can get at those raw values. We can also actually point to geotiffs in some cases directly on the server and get at their raw values as well. Okay, and then there's just a slide showing the our instrument localization pipeline, how we break it down into mass instruments, fixed instruments, and then contact science instruments. And then this is a case for MSL where we break out the various mass instruments, fixed body, and contact science. And again, we feel like that pretty much covers every type of instrument, more or less, that you could expect on any spacecraft. So it's a lot of back-end things there, and then now here's the front end. So as a geologist, you know, we like to see things in different views and to get our perspective. We have our, so in this case, we have 3 unique views of the data panels. So we have the kind of the map panel or map view, which is your default view, your typical looking from orbit straight down to the surface. We also support a 3D view, which is linked to that, or global view. So we can browse around in 3D as geologists are wont to do. And then we also have an in situ view, so we can actually look at data that's taken from the ground and see it from that perspective. In this case, the rover's perspective for MSL. And then importantly, we're also linking to data. So instead of searching through a bunch of different other just wiki pages and have to scrape them and reformat data and link it to your data sets, we're actually linking it automatically within MMGIS. And so I'm going to show you some examples. Let me just show you the test case for MSL, which really was kind of our running definition. So this is a slightly older version of MMGIS, but the functionality is pretty much all there. So basically, we have our high-rise base map in the background, and we have the traverse of MSL in white. The black dots are the various waypoints, and if you click on one of those waypoints where the rover stopped, you automatically link to the ground view, and which we have opened up in the in situ panel, our viewer, and you can see we've basically taken a cylindrical mosaic from the ground and wrapped it into a photosphere, and that allows us to actually show features undistorted from the point of view of the rover. And you can see as we click to the next position, we automatically load a new mosaic for that position and overlay targets where the rover has done some science, either taken a picture, taken some chemistry observations, or done some contact science. This is gonna, let's see, always be a little bit faster. Yeah, so as we zoom in, we scale in different data sets. So in this case, the green dots are ChemCam points, so we automatically see the target name. When we click on them, we can then open up our chemistry browser, and this shows basically, matched via data table, the oxide values for each of those points. And this is the quick look data. So this allows you a quick way to get into those chemistry values, see what they are. We can just mouse over them, and you get these kind of percentages of the oxides thereof. And then you can resort them to compare each of the shot points and see where some oxides are more present than others. But importantly, we've also linked these views together. So not only can you see this data in 2D, you can also see it in 3D, and then begin to look at where this data occurs in an elevation context, as well as a linear context from point to point. All right, I'm going to skip ahead a little bit in the name of time. Oh, you can do it. Oh, okay. I see. Okay, this is just showing a measurement tool. So interestingly, we kind of overloaded this to do three different things. One, you get a distance. Second, you get an angle. Three, you get a profile. Because I was constantly being asked, I need a profile of this area. And I'm like, no, move the point a little bit. You know, which is all good and fine, but it required me to constantly being in the loop. So this allows saves time. And actually, a newer version, you can actually download this data directly after you've made the profile measurement. Okay, moving right along, just to show that we're not just all ground data, here is Mercury. This is data we just imported the base map and some elevation data in the background. It works the same. MMGIS is planet independent, we really don't care. Now, it is geared towards spherical bodies. That would probably be its limit. Might be hard to do this with a small body. But you can see here, the tools basically work the same. It makes a measurement, it just uses a different coordinate reference system, and we get the same profile tool that can look at the data. Then I'm just going to show, we're going to turn on some footprints. This is about prints. And what we've done is we've created a URL inside of the footprint file. So we can just click through the files and that data is automatically served. And this data doesn't have to be local. We're actually pulling images straight from the PDS, their thumbnails. And you can see that we can kind of zoom in and just click around and get a simple, quick view of the data sets that are available. Okay, just gonna highlight totally different planet. Okay, and then just showing we have the 3D view there. So we can do things at various scales. I'm gonna move on to, now here's an example of MMGIS with Enceladus. Again, we don't care. Moon, planet, all the same. So here we're looking at tiger stripes, the Damascus tiger stripes specifically on Enceladus. And again, the measure tool works exactly the same. We can mouse over, see the raw value points. We're just gonna see if I can click ahead a little bit. Now here we've turned on a slope layer, so we can have various layers that we can overlay. And let's see. Oh, okay, and we're just showing here the 3D view again. And so these views can be actually linked together. So when you move one, you move the other. I'm just gonna highlight, let's see, yeah. So we're gonna turn on roughness here. You can see we're actually using the same data set to be shown in 2D and 3D. So we're not really having to create two different formats. We're really using just one format and overlaying it on top of the other. And here we're actually looking at raw values that we're mousing over for this roughness data set. So we're actually poking right into a raw data set, just using its geospatial location. Now the cool thing is, if you ever want to know what it's like to walk in Enceladus, well, here's what it's like. So we have this walk mode, which basically simulates your view shed. And as you move around, you can see on the left-hand screen, there's a green dot. And you see on the right-hand screen also, that's where that dot is actually intersecting the surface. So we're doing the ray tracing. So you can get an idea of like, you know, how far away is that mountain? What am I really looking at on the map? What am I seeing? So you can imagine in terms of a looking on the ground, this is a pretty useful tool to know where you are. So we took MMGIS and we adapted it for the InSight mission. It was used during operations to support the placement of the seismometer size and the HP3 heat probe on the surface. And so instead of the project building a whole webGIS system and then building a tool to place the instruments, we just built the tool. Or I should say, more importantly, Tarek Solomon was the main developer here and did most of the work. The vast majority of the work, I should say. So here again, we're turning on other layers. We're showing placement properties. The instrument outline is the actual size of the instrument based on the CAD drawings, and we can simulate the placement and start to poke at values around it. We can also look at error matrices. So this little widget showed basically kind of like the horizontal offset that you might want to control in terms of how much you think the placement property is good. We can also control the amount of yaw that the instrument would change over. And we'll move on and click forward a little bit just in the name of time. We were actually simulating both instruments as well as the heat shield. So we could put the seismometer on the ground and then save that to a database, which was then fed forward into other tools like Mars Viewer. and RSVP, which is the robotic software that we use. And again, we can show this data in 2D and 3D. And the fun part is we actually imported, let's see if I can get ahead here, imported the CAD models. And then as we moved one model, as we moved the placement, it would actually change the position of this instrument in real time. And so we kind of get both a, you know, the 3D is really nice to give you the scale of what's around you. And so it's really nice to be able to show that in 2D and 3D and move this instruments around, actually both instruments, in a workspace and see how they fell. However, the MMGIS tool was used to make actual critical measurements in terms of heights of rocks and distances from other features to determine the safety to meet the requirements for placing the instruments on the ground. I do have one more slide, but you know, in the interest of time, since I'm kind of at my 20 minutes, I'm just going to let it run and leave it open for questions. Actually, I should probably stop sharing so you guys can ask questions. So I'm going to do that.
We can come back to it after too.
Yeah, sounds good.
Does anyone have a quick question? We can also have a long discussion after Jay's talk.
I do. Yeah, I guess I called dibs there. Are you planning on integrating any webVR tech into this? So I know there's something called OnSite with the HoloLens, but there's also some of these augmented reality and web virtual reality toolkits that work with Chrome. So you're able to just like plug in your VR headset, right, to your desktop and get that data without some ridiculously expensive AR headset.
Right. Yeah. So I'll talk real briefly, and then we can probably let Jay go and then ask questions afterwards. Yeah. So we experimented with we don't, a couple things we didn't want to do. One is not to compete with OnSite because there was just no way that would be possible. But what we recognized was that low-cost VR with very simple low-cost headsets were probably a good way to go. And we experimented a little bit with that, but we didn't have quite enough time to develop it fully. We do have a little bit of AR actually in our application. So there's a case when you look at that photo mosaic, you can actually use your tablet like a window and spin around that mosaic and look up and down. That to me, that kind of like portal VR or tablet-based or even phone-based AR is pretty exciting. So we had a few demos, we did it. The code's in there, you could play with it. We don't advertise it too much as an actual feature, but there is a little bit of experiment there. I think that's where, because really the thing is like the cost, right? I mean, a HoloLens is, $1,000 or more. All the other nice headsets are also a few $100s, and then you have to distribute all that stuff. But like, everyone's got a phone. A lot of people have tablets. That was a much easier mechanism to use VR or really AR, I think, in terms of, or some hybrid of VR and AR in that circumstance is a lot better way to go. Anyways, I'll stop talking and let Jay take over.